Today's class begins with the structure of the earth and the plate tectonics. So for the contents, we have the introduction to the structure of the earth, different layers of the earth, plate tectonics, plate movements, Wilson cycle, plate boundaries, and a summary of the topic. So firstly, if we come to the point like structures of the earth. So we know there are three different layers. Those are the crust, mantle, and core, as we know. But physically and chemically, we can differentiate both. Physically, if we talk about, physical means based on physical properties. As I have said, physical means rheologically. Okay. Based on the rheology, that is the state. What is the state of that particular, means is it physically solid, or is it in a molten state or semi-molten state? So in that way, we can differentiate the different layers, or we can say that there are different layers. Those are lithosphere, asthenosphere, mesosphere, or the mantle, outer core and inner core. Based on the chemical properties, that is the chemistry or the compositions of the different layers, we can say continental crust, there is oceanic and seatic, oceanic crust, upper mantle, lower mantle, outer core, inner core. So these are the differences. Okay. Now, when we talk about the earth, we have to know what is the shape of the earth, right? Because the volume, we have to know about the volume. So when we talk about the shape of the earth, that is the sphere. Means earth, we know it's spherical, right? We say it's a spheroid or sphere in nature. But actually its shape is known as oblate spheroid. It's a very important question which we get in JAM. What is the shape of the earth? That is oblate spheroid. Now when we talk about the crust, so when we talk, the first layer is the crust. So crust contains the continental crust and the oceanic crust. Within the continental crust, we have the oceanic and the seatic layer, between which there is a discontinuity surface that is known as the Conrad discontinuity surface. Why this discontinuity surface has been created, right? First of all, we recognize the discontinuity surfaces based on the velocity of the body waves. It can be P wave, it can be S wave. But P waves moves faster compared to S wave. We will deal with the P waves, velocity of the P waves, how the P waves velocity is lowering or increasing, or for the velocity of S wave, how it's increasing. But as the densities increases, that therefore the velocity is also increases. That's the fact. So Conrad discontinuity is a local, it is a not the major discontinuity, it's a sub-branch discontinuity where it's because of the change in the chemistry. That is, this is sialic, that is silicate rich, and this is seatic, that is a more mafic rich. Between those, we have the Conrad discontinuity surface. Then the continental crust thickness 10 to 70 kilometers, less dense mediums, lesser than the oceanic crust, and mostly old. When we talk about the oceanic crust, what happened the oceanic crust? Okay, between oceanic and seatic, oceanic is lighter and seatic layer is mostly very dense. It's a denser medium. Whereas in case of oceanic crust, it's much more denser. It is made up of what? It is basaltic in nature. Okay, it's basaltic in nature, and continental crust is mostly granitic or granodioritic in nature. Okay. So when we talk about this different rocks or chemical compositions, etc., these are the minerals. So we have to know what a mineral is. It's a naturally occurring homogeneous solid having a definite ordered internal structure. That means it should be crystalline in nature. One more thing which I have mentioned over here, what is the last age, or what is the oldest oceanic crust that we observe on the earth till now? That is Jurassic, which gives where from we get this answer? We get this answer from the Wilson cycle. Wilson cycle tells us about the story of how oceanic crust has been disappears, how new oceanic crust forms. It tells about the story of the cycle of new oceanic crust. So that is formed through Wilson cycle, which is a cycle of 180 to 200 million years. That's why 180 to 200 million years. That's why the last oldest rock or the oldest oceanic crust which we observe belongs to the Jurassic period. Okay. Now when we talk about the mantle is the, if we talk about volume wise, it is the most 80%, 68 to 75% of the volume of the earth is given by the mantle. It is divided into the upper layer and the lower mantle, upper mantle and the lower mantle. Within the upper mantle, there are the transitional zones up to 700 kilometers, because below 700 kilometers, the nature of the rock, that is the brittle nature, changes to ductile nature. It becomes ductility. Therefore, the deepest earthquake which we observe on the earth, it is still deepest earthquake. If we talk about the deepest earthquake, that is 680 to maximum 700 kilometers. Okay, within that we observe that. This is an important question for JAM, for MCQ type of questions. Okay, and so mantle is the layer which is mostly peridotite in nature, peridotic in nature, that is dunite. It can have Fe, chloropyroxene, orthopyroxene, then olivine. These are the materials which is made up of it. So it's a much more denser. Therefore, gradually when we go down to the mantle, we get higher values of velocities. Okay, P wave velocity. The maximum. So if we go through that, and then comes the core. Core is 33% of the mass of given by the core. It's mostly made up of outer core and inner core. Outer core is hot fluid in nature, hot liquid, whereas the inner core is solid. And this fluid nature of this earth is, that is the core, this is fluid. Who gives us the answer? That is the velocity of S wave here is 0. As we know, S wave cannot propagate through fluid. So that's why where S wave is not found over here, that's why we can say the outer core is fluid in nature. Outer core is liquid, we know that. Inner core is solid, it is the metals that is made up of. Here this diagram is important. When I was teaching, I already have told you, there's the velocities. This is taken from Lowry. Okay, you can go through this picture where the values of the P wave velocity, the P wave and the S wave velocities is very much essential, because the values come in JAM examination. Okay, so what is the velocity of P wave at 410 kilometers, below 400, or where is the deepest highest velocity of P wave is observed? That is at the D double prime layers. Okay, that is the core mantle boundary, where 13.7 and 7.2 is the velocity of the S wave. And here you see no S wave, there is no S wave present over here. So that's why what we can say, no S wave, that's why it is fluid in nature. And we will see drastically there is lowering in the velocity of P wave. Okay, it drastically lowers down. Maximum reaches up to around 8.4. Then it will be higher, more. Here up to 11 it can go in the inner core, but here it is lowering. Okay, and these are the different layers: asthenosphere, Gutenberg layer. Gutenberg discontinuity surface is between the core and the outer core and the lower mantle. Okay, this is the Gutenberg discontinuity surfaces. And other thing which was I was teaching during when I was teaching, I already told you that what drives the plate? What drives the plate? Drives the plate to move. Okay, the convection cycle. Here are at the mantle, there are the convection cycle which drives the plates, which makes the plates to move. Okay, so this plate movement is driven by the heat within the earth as well as the convecting cycles which are being carried out. That helps in that. Okay, another point is this is the P and the S shadow zone. P wave or the P shadow zone. P shadow zone varies from P wave where the P velocity is not been observed. P shadow zone. Okay, we don't get the P shadow P wave velocity, though that belongs from 104 to 142 degrees, whereas for S is from 103 or 104 up to 180 degree. This is the S wave, means S shadow. Now, as we talk about the different layers and how we are understanding this, because of the geophysical surveys which are taking place. We do the geophysical like sending of the P wave, S wave velocity. We measure where is the P velocity, what is the velocity is coming back. It helps us to understand that. So these are the different seismic velocities. These are magnetic anomalies and the electrical anomalies helps us to understand about the different layers of the earth. So this is the world scenario today. As we can see, Pacific oceanic plate, it has reached it to its maximity. Okay, after that what will happen? It will get subducted, it will demolish. Okay, this Pacific will get to demolish, whereas the Atlantic, which just formed during the Jurassic, Atlantic started to form during Jurassic, late Jurassic. So it is still at its teenage period. Okay, it's going to be adult next. So it will increase, and at the baby form, or as we can say, very small, that is the Red Sea, which is expanding day by day. So it can happen that one day the Pacific won't be there, Atlantic would reach its maximity, and the Red Sea will be like the Atlantic. So this way we can say how the different supercontinents is taking place. Like we thought the last was Pangaea, before that was Pannotia. So these are the different super continents which take place, or which supercontinents are formed because of the movements of those plates. Okay, and this movements is again driven by the in itself, means present within the convection cycles which are taking place, that drives the plate. Okay, different plates, and these are the different tectonic regions which I've already mentioned. And this is the plate convection cycles. So the outer core, another important question, that is the outer core fluidity, means outer core's liquid nature. It also governs the magnetic property, or the magnetic layers, or the magnetosphere. It governs the position, or the energization, or the magnetic property of the earth is governed by the convecting cycles of the outer core. This is also an important question which came in JAM earlier also, that what governs the magnetic layers, or the magnetic property of the earth, magnetic magnetosphere of the earth, that is the the convection cycle of the outer core, as well as the sun, or the solar heat, the sun, the solar winds, which also governs the value, or the magnetosphere of the earth. This is the Wilson cycle, as we know. So in the Wilson cycle is a cycle, as I have said, it is a cycle of 200, maximum 200, 180 to 200 million years cycle. It starts with what? It was a stable, like this is a stable platform, means this is a like this is a stable platform. Now what happens, as we state, this is a cratonic part. Okay, this is step 1. In the step 2, what happened? A rifting takes place, that is an extensional setup takes place. Rifting takes place. As the rifting is taking place, rifting is increasing, and what happened? Mid-oceanic ridges are taking place. So new oceanic plate is being formed. So when this oceanic plates is formed, new ocean boundaries also form, new oceans takes place. And after that, what happens? It reaches its extremity of extension. Then what happens? Subduction, because the volume of the earth is fixed. So subduction takes place, and at the subduction points there is the compressional setup. Therefore, what happens? The oceanic boundary which was being formed, or the oceanic plate which was being formed, it is getting subducted. It is being narrowed day by day, and it would happen like this. What it happened took place between Indian plate and the Tibetan plate. What happened? The Indian plate, between Indian and the Tibetan plate, was the Tethys Sea. Say about this was the Tethys Sea. And this Tethys Sea got disappeared day by day. And this Tethys deposit is nothing, the Himalayan mountains which we see. All the sedimentation which took place during the Tethys period, that is the Paleozoic and in the Mesozoic period, those deposits only we see in the Himalayan range, right? Those are the fold belt mountain chains forms. And what happens? Subduction is taking place. So Indian plate, when this subduction taking place, the Tethys Sea was getting disappearing. At the point of time, what will happen? The ocean will disappear, like this condition. No ocean is present. So now the two continental crust coming closer to each other. And what happened? They collide against each other. and thrusting takes place. Either one of the one which is more lighter, that will go up, or the one which is more denser, that will go down. In the case of Indian and the Tibetan plateau, what happens? Indian gets subducted under the Tibetan plateau, and it's subducting till today. So due to this subduction, so that's why there was a question, what type of falls do we observe or do we see in the Himalayan range? Those are mostly thrust falls. Okay, thrust falls is the maximum falls which we observe in the Himalayan range. This is an important question for MCQ type of question. So due to this collision, what happens? Fold chain mountains will form. Here fold chain mountains is forming. Two continental crust is coming. So two continents cannot get disappeared, right? So they will fall fold chain mountains. And with the time, what will happen? They get eroded, and again a plate or craton will be formed. So this is the total cycle of Wilson. So these are the different stages. This is the earliest stage, like now in case of the Red Sea, or where the Eastern African Rift system has been present. Okay, one thing I would like to mention, please try to remember the example, present examples. Like when we are saying, like in the embryonic stage, it belongs to the Red Sea along with the East African Rift system. After, these are the points we should remember, because these quick, very new names, the name is coming in examination for MCQ type, not MSQ, for MCQ type of questions. Okay. Now Red Sea is expanding. So for the mature stage, as we observe in the Pacific, that is in the mature most stage it is in. Then what will happen? There will subduction will be taking place, like in the case, like they are saying in Mediterranean Sea, there was a subduction was taking place. Another stage, that is the best example, Indian and the Himalayan, where the fold bed chain mountains will be forming. So now we come upon to the different plate boundaries. Okay, what are the plate boundaries we can see? One is divergent plate boundary, one is convergent plate boundary, another one is transform fault. So divergent means where new plates are formed, new plates are taking place, or new plates are formed. Convergent, where destruction is taking place. So these are known as destructive and these are known as constructive. Okay, and these are transform fault or strike slip faults. So there is just slide movements, no destruction, no nothing, no new plates are being formed. So divergent plate boundary example is MOR, right? Mid-oceanic reach, where the spreading reach, where the more basaltic magma, we get the most basaltic magma from the ridges. Okay, here the geothermal gradients, high geothermal gradients are at shallow condition, at the shallow state. Okay, and this shallow, there is a question also, like where is the gradient, means geothermal gradients get at a shallow stage, or where the geothermal gradients get deepened or get they just subduct, means in the subduction zone, what happened? They get granulated or they get lowered. Okay, so what happened? As we see here, we will get high, like for example 500 degrees centigrade geothermal gradient, or to 1000 degrees centigrade geothermal. There is shallow depth. Okay, that is in the divergent. And best example is Iceland, which we see on the surface, the east, the Pacific. These are the convergent plate boundaries. There are three types of convergent. One is continent-continent, there is continent-ocean, and ocean-ocean collision boundary. Okay. This is continent-continent, as in the case of fold mountains will be formed. Okay. Next, continent-oceanic collisions, continent like Andes, between, means the Andes when they were formed. So one was oceanic plate, another was the the continental plate. And in the continental crust, what happens here? The mantle wedge. Here, what happens? The geothermal gradients get perturbed. Perturbed means they get lowered. Okay. For example, here the temperature would have to be around, say, 600 degrees centigrade. But due to this perturbation, why this perturbation takes place? As this plate is getting subducted. So there we have hydrous minerals. Okay, hydrous minerals. What happened? Those minerals at this, like hydrous minerals are stable at lower temperature pressure. When they are going deeper and deeper, they are not stable, right? Devolatilization or decarbonization takes place. So volatile materials get removed from the structure. So due to this, what happens? These geothermal gradient gets lowered due to the presence of this volatile and the what means volatile materials. There is perturbation. Perturbation means lowering of this geothermal gradient. So suppose here at this point, at this stage, at this depth, the temperature should have to be 1000 degrees centigrade, but you are observing of geothermal gradients say 700 degrees centigrade. So this is perturbation. So the geothermal thermal gradients are getting deeper and deeper. So examples such as Andes. And ocean-ocean collision, that is Mariana Trench, the deepest trench that we observe on the earth, that is Mariana Trench. And the height between the highest is Mount Everest. Distance between Mount Everest and the deepest trench together is known as the Challenger's depth. Now for the case of transform fault, they just move side pass. You can see one block is moving this side, other block is moving this side. They are just slide past each other, due to which earthquake will be forming, but no new plates will be formed. No formation or destruction of the plates will be taking place. Such example is San Andreas fault. So these are the different layers as we see. We can see mainly 3 core mantle crust, and the plate tectonics are moving slowly, driven by the driven by the convection cycles through the mantle wedges, through the mantles. Also, we can say the different types of, there are 3 different types of plate boundaries: convergent, divergent, and transform faults. Okay, so volcanoes and earthquakes are associated with. So now I come upon to the questions. So this is the first MCQ, NAT numerical problems which I am dealing with. First question is, during concretionary growth of a spherical grain of radius 2 angstrom, the rate of change of surface area with respect to change in radius of the grain is. You have to find the rate. What is your question is asking? Find the rate of change. Rate. Something rate means some sort of, and rate of change with respect to what? Change. Rate change of radius. Why radius? What is this concretion? What do you mean by concretion? There is a nucleus. Some sort of nucleus. Say it can be a fossil also, it can be a brick also, anything. Above this nucleus there is growth, that is some sedimentation takes place. With time gradually what happens? Sedimentation increases. So this concretion also increases, right? So what happened with time? We are getting more and more larger and larger diameters. So with the change in diameter, like this was say 1 centimeter, then it became 3 centimeters, suppose they became 6 centimeter. Gradually the diameter is increasing. So with what rate the sedimentation, like the change in surface area, total surface area, how the surface area is changing with respect to the change in the radius. You have to find that answer. So for that we have to know just mathematics here, that what is the surface area of a sphere. I have already written over here, that is equals to 4 pi r. This is the equation which you require. No geology is required over here. So 4 pi r. Now why then we have to say this is the change with respect to radius. So if we do respect to radius means dr, means if we differentiate the change of surface area, so we are differentiating the surface area this side, therefore we have to differentiate this also, pi r square. So if we differentiate, we will get what? 8 pi r. So if we now just put the values like 8 into 3.142 into r is what? The initial radius was 2, so 2, and then we will get this answer. That is 50.24 by 10 to the power 8, right? So 1 angstrom, we have to know this also, equals to 10 to the power minus 8 centimeters. So the answer is in centimeters. So 2050.24 into 10 to the power of 8 centimeters. Next, this one is another very simple question, that is, refer to the schematic diagram or sketch. Assume average saturated density of the oceanic crust. Suppose the density of the oceanic crust is 3200 km per meter cube, whereas the density of the water is 1000 kg per meter cube, right? That is given. And acceleration due to gravity, that is 10 meter per second square. The overburden pressure at point P. Where is point P? Here is point P. So what are the pressures you are getting? You are getting the pressure of this lithostatic pressure as well as this hydrostatic pressure. So thickness of this unit is 2 and thickness of this water unit is 2. So total distance thickness is 4. That's why 4 kilometers thick. So now you have to just calculate the overburden pressure. How much pressure is there? So total pressure is equal to rho GH. So here the two different units. One is with water, hydrostatic. For hydrostatic pressure you are giving rho water GH plus of rho of the oceanic crust, right? Rho of oceanic crust into G. Just calculate it. Whatever the answers will come, like 8, 4, 1, 2, 3, 4, 5, 6. 6 knots will be coming. So 1 megapascal is equal to 10 to the power of 6 pascals. So here the answer will be 84. First of all, you have to see whatever the questions they are asking, in what unit you have to give the answers. Based on that, if your answer is wrong, the answer will be wrong. You have to see the unit they are asking. That is also an important thing in JAM. Okay, another question. This is also based on rate. This is at what rate uplifting is taking place. So this is a schematic diagram. Okay, this is the present condition of the river. Here is the river water present over here, and this is, here is the sample. Say location 1 is the sample from where you are taking. This is the location point. Okay, and it is, this is 100 meters. So this thickness, it is situated at around 400 meters above from the surface, right? So 400 meters. Now let's see the question. In a structurally controlled fluvial system, so structurally controlled fluvial system means faulting or fracturing is taking place, then there is a fluvial system. An asymmetric flight of river terraces. See, 1, 2, 3 means with deformation 1 took place there, then this was the height. Then deformation 2 took place, this was the height. After deformation 3rd, this is the height. Okay, shown in the figure was sampled at location L1. So L1 is located here. The age of the sample was 30 Ka. Ka means 10 to kilo year. Ka here means kilo year, that is 10 to the power of 3 years. So into, that is equals to 30 into 10 to the power 3 years. Why we are doing in years? Because the answer they are asking in millimeter per year. Again I have said the unit. Assuming that the terraces were formed entirely due to deformation. Due to deformation means due to upliftment. These terraces were being formed like steps what we see, like shiri what we say. Related upliftment and average uplift rate. You have to find the average upliftment rate. What was the rate at which it was moving? So anything rate means at which it was moving, that is distance by time. So here what is the distance it had moved? From 100 meters it had moved to 400 meters. So total distance, how much it had moved? 300 meters, right? That is 400 minus 100, that is 300 meters distance they have moved. Now you have to find the rate. So for the rate, average rate were there, distance by time. So distance is 300 meters and time is 30 kilo years. So since they are asking the answer in millimeters, so meter to centimeter, meter to millimeter you have to put it. So what is it? So 300 into millimeter, when we have to do meter to millimeter, then it will be 10 to the power 3. And here also 30 into 10 to the power of 3 years. So if we just calculate it, it will be 10. So answer is 10 millimeter per year is the answer. This is another question. In an oceanic basin, a 4 million-year-old oceanic crust lies 40 km away from the ridge axis. The average velocity in centimeter per year of the oceanic lithosphere is. So this is the, again I am drawing this. This is the mid-oceanic ridge. Okay. What happens from here? When magma is getting out, this side will be one flank, this side will be another flank. Again, when second set of magma, this place will be moving. So at what happened? Each time magma is getting erupted over here, new magma, the old magma is moving apart and it is giving space for the new set of magma. So what happened? Now you have an oceanic crust or oceanic basin here, whose This is the ridge axis. From ridge axis is distance is 40 kilometer away. Okay, 40 kilometer away. And now 40 kilometer away, and the age of this oceanic crust they are saying is 4 million years. mm is million years. So 40 kilometer, they have to find the average velocity. Again velocity, that is distance by time. So here distance is 40 kilometer and they are asking in centimeter per year. So here, so kilometer to, you have to put it in centimeters. So kilometer to meter and then centimeter by year. 10 to the power 6 million years means 10 to the power 6. So 306. So 10 to the power 6, that is equals to, rate will be 1 centimeter per year. Okay, till this much, this is the question. Next we will decide next.